Find a derivative using implicit differentiation. Our objective in this lesson is to find a derivative using implicit differentiation. So far, we have been taking derivatives of explicitly defined functions. These are functions where the y is already by itself on the left side of the equation, such as these that you see here. Y is only on the left side, and the other side may have the variable x or another variable in it. Sometimes we will be encountering implicitly defined functions. These are functions where the x and y might be collected all on one side or a mix on both sides. These are examples of implicitly defined functions, basically just thinking how the y is not by itself on the left side of the equation. The first two implicitly defined functions can be defined explicitly. Notice if we take this equation and we add 4 to both sides, so we have xy equals 4, then we divide by x, that leads us to an explicitly defined function. Also, this equation, we can subtract the 3x squared and add the 1, so y squared equals 1 minus 3x squared. And then taking the square root gives us two explicitly defined functions, the positive square root of 1 minus 3x squared and the negative square root of 1 minus 3x squared. So if we need to find a derivative, and the function is implicitly defined, it is possible that first we explicitly define the function by solving for y, although sometimes that may be difficult because, like in this one, it leads to two equations that we would have to differentiate. Now, this third example of an implicitly defined function cannot be solved for y. Notice where these y's are located in this implicitly defined function. Find dy dx if xy minus 4 equals 0. So we talked about how we can solve for y and get an explicitly defined function, but sometimes we can't, like that third example above. In that case, we would have to use implicit differentiation. What will this look like if we use implicit differentiation to find dy dx? So finding dy dx means we want the derivative with respect to x of y. So that's what we will do with this equation, is find the derivative with respect to x of both sides of the equation, xy minus 4, and the derivative with respect to x of 0. We're taking the derivative with respect to x of both sides of the equation. Now first we encounter a product, x times y. So when we take the derivative of that, we are required to use the product rule. Remembering our product rule, fg prime plus f prime g, f will be our x. So x times g prime, the derivative of y, which is d dx, the derivative with respect to x of y, plus f prime, the derivative of x, d dx of x, times g, which is y. This is the derivative with respect to x of that product. Then the derivative with respect to x of 4, since 4 is a constant, that derivative is 0, and the derivative with respect to x of 0 is 0. Let's do some simplifying. The derivative with respect to x of y can be written simply as dy dx. X from here times dy dx plus the derivative with respect to x of x is just 1. We could think of it as dx dx, and that would be another helpful way to see that it's just 1. Times y Minus 0 equals 0 simplifies to simply equal 0. Now remember, our goal is find dy dx. That means in the end, I need my answer to say dy dx equals something. So I need to get dy dx by itself. 1 times y is the same as just saying y, so we can subtract y to the other side. Now we have x dy dx equals negative y, and then I can divide by x to get dy dx by itself. Dy dx equals negative y divided by x. And there we have dy dx. What does it look like if first we solve explicitly for y? So remember, x, y minus 4 equals 0 leads us to y equals 4 divided by x. I would prefer to not have to use the quotient rule, so I'm going to bring the x up and rewrite this as y equals 4x to the negative 1 power. Now I can simply use my power rule to find dy dx. Multiply by negative 1, I get negative 4x to the negative 2, and then I can rewrite this without negative exponents, negative 4 over x squared. And there I have dy dx. Now notice, this looks different than this, but in fact, they are the same thing. Let's see why. This has only x's in it. This has a y and an x in it. Remember how when we explicitly solved for y and we got that y equals 4 over x, we can substitute that into that spot. So let's see how that looks. Negative of the y, 4 over x, and then divided by x. That's the same as saying negative 4 over x times 1 over x, which is negative 4 over x squared. So you see, both of these derivatives are the same as each other. It's just they were in different forms. Both of them are acceptable as final answers. This is a valid answer for dy dx, and this is a valid answer for dy dx. Sometimes we're able to solve explicitly for y first, sometimes we are not, in which case it's important to know how to use implicit differentiation. Find y prime equals dy dx using implicit differentiation for 2y equals x squared plus sine y. Now sometimes I think, can I solve for y first to make it an explicitly defined function for y? In this case, I can't, or it would just be too much work. So let's go ahead and just start taking the derivative with respect to x, that's what my goal is, of both sides, 2y, and the derivative with respect to x of x squared plus sine y. Now we take our derivative of 2 times y. Well, 2 is a constant multiple, so it's 2 times the derivative of y, which is just dy dx, equals the derivative of x squared is 2x. The derivative of sine y is cosine y, but this is not a function of x, this is a function of y. So I have to think about using my chain rule. Notice that my variable is y, but I'm taking the derivative with respect to x. Just like over here, when the function is y and I'm taking the derivative with respect to x, I have dy dx as part of my derivative. Over here, I have cosine y, and then the chain rule, the derivative of the inside, dy dx. Now remember, our goal is to find dy dx. That means I want my answer to say dy dx equals something. So I need to collect all of my dy dx to one side, just like when I'm solving for any other variable. This has a dy dx in it, this has a dy dx in it, but this does not. I'll bring this over to the other side by subtracting. So I have 2 dy dx minus cosine y dy dx equals 2x. Now I factor out the common factor dy dx. 2 minus cosine y is left. And now I want dy dx by itself. It's multiplied to this binomial, so I will divide by that quantity. Dy dx equals 2x over 2 minus cosine y. And now I have dy dx. Find an equation of the line tangent to the graph e to the y times cosine x equals x plus 1 at the point 0, 0. Now remember, when we want an equation of a line, the things we need are a point, which they gave us, and a slope. We don't have that yet. I need the slope, which we often call m, but we also call dy dx, the derivative of y with respect to x. Notice our implicitly defined function. It will be easier to take the derivative implicitly. So I take the derivative with respect to x of both sides, e to the y times cosine x, derivative with respect to x of x plus 1. Notice over here, I have a product. I need to use the product rule, e to the y and cosine x multiplied together. So my product rule, e to the y as it is, times the derivative of cosine x, negative sine x, plus the derivative of e to the y, which is e to the y, but because I'm taking the derivative with respect to x, and that has a y in it, I have to use my chain rule. So e to the y times dy dx. Cosine x as is. There's my product rule. The other side of my equation now, derivative of x is 1, derivative of 1 is 0. Notice this is x and this is x, so I don't need a chain rule. I notice I have dy dx only in this one spot, so I can move this to the other side. Let's simplify first. Negative e to the y times sine of x plus, I would probably prefer to rewrite this as e to the y cosine x times dy dx equals 1. This can get added to the other side. So e to the y cosine x dy dx equals 1 plus e to the y sine x. Now I want dy dx, so I need to divide by that, which is multiplied to it. Dy dx equals 1 plus e to the y times sine x over e to the y times cosine x. Now remember, my whole reason for finding dy dx is I needed the slope. This is the slope, but it's at all xy points. I want the slope at that point of tangency, 0, 0. So we are going to find dy dx at the point 0, 0. This is notation to show that we're plugging in 0, 0. 1 plus e to the 0 times sine of 0 over e to the 0 times cosine of 0. That makes 1 plus e to the 0 is 1, sine of 0 is 0, e to the 0 is 1, cosine of 0 is 1. So that looks like we get 1 plus 0 over 1, which is 1. So our slope is 1. Now we can write the equation of our tangent line. Y minus the y-coordinate equals 1 times x minus the x-coordinate. This is an acceptable equation for the tangent line. However, you can definitely clean this up a lot. This simplifies to y equals x. And there you have it.